All right. Hi, everyone. Welcome to our 37th session of MedAI Group Exchange. This week, we have Misha from Carnegie University here with us to present his research on federated hyperparameter tuning. Misha is a PhD student in computer science at Carnegie Mellon University, advised by Nina Balkan and Amit Tawalkar. His research focuses on foundations and applications of machine learning, in particular, the theoretical and practical understanding of meta-learning and automation. He is a recipient of the Facebook PhD Fellowship and has spent time as an intern at Microsoft Research New England, the Lawrence Livermore National Lab, and the Princeton Plasma Physics Lab. Thank you, Misha, for joining us today. Before we start, could you let us know your preference on how you want to take questions?
I'm happy to take questions while I give the talk and then at the end as well.
Sounds good. So as always, let's try to make this session as interactive as possible. Without further ado, let me hand it over to Misha.
Thank you, CU, and thank you for the invitation. I'm very happy to be speaking here. Today, I'll be talking about our work on federated hyperparameter tuning, some initial explorations we tried to make of this challenging area, the baselines we've discovered, and some connections to an area of machine learning called neural architecture search and the technique of weight sharing there. So as many of you probably know, machine learning has really evolved a lot over the past decade or so in the scope of the applications to which one can think about actually applying these statistical methods. So for example, cell phone devices, Internet of Things devices, smart homes, medical data, and so on. And this is all great, but the issue is that many of the algorithms that we use in machine learning for the past 20 plus years have really been built with this assumption that you're going to be training everything in a distributed optimization cluster in a data center. So where you have all the data is local, you have very fast access to it from very powerful machines that can train very quickly. This is the general setup in academic labs and research labs in industry and so on. Unfortunately, in practice, we have a lot of different types of data where we can't actually do this. So for example, on cell phone data, we don't want to send user device data to, say, a corporation that wants to learn how to do autocomplete on your cell phone device. You don't want your data to be sent directly to them, just raw. Similar privacy concerns, of course, hold for IoT devices and smart homes. And then there's an entirely separate setting that many of you probably are interested in, of the medical setting, where you might have very strong servers in these hospitals, but you might also want to learn from multiple hospitals at a time to learn better machine learning models across all of them. And so, over the past 3 or 4 years, a new setting or even paradigm of machine learning called federated learning has been developed to be able to actually train on edge devices and basically multiple devices that are massively distributed, so distributed possibly all over the globe. They have very heterogeneous nodes, so some cell phones might be very weak, some hospital clusters might be very strong. They have sometimes very small sample sizes. Sometimes I don't text very much maybe, and I use a different messaging service, and so the text data might be very limited. But on the other hand, other people might have very large samples. The samples are non-IID, so I text very differently than you might text. And there are very strong privacy considerations here as well, especially, for example, in medical data, and of course, also mobile device and IoT data. And so to train on these edge devices, we have to develop new algorithms to be able to handle the fact that it's massively distributed and we have very weak devices. Our regular algorithms are just going to cut it. And similarly, as we'll see in this talk, our regular hyperparameter tuning algorithms also aren't going to cut it. But people have already developed regular algorithms, not hyperparameter tuning algorithms, for this federated learning setting. And so we're going to study how to tune the hyperparameters of these algorithms in a good way. How do we actually do this? And to do this, we should probably introduce first an actual algorithm for federated learning that we'll focus on, although our algorithms don't have to be specifically applicable to this algorithm. And this is the Federated Averaging algorithm from McMahon et al. In 2017. It's an AI stats paper. And the idea here is you want to train a global model from many devices. A global model, say, to predict the next word, like an LSTM or a transformer model, to predict the next word in your text message. And the model they have is that they have a server that initializes the model, and this server has access to a batch of devices. So for example, a batch might be the cell phones that are awake, so say plugged in and not turned off at some time, that are available for training. And the server is going to send its initial parameter of, say, a neural network, W0, to this batch of devices. And each device in this batch is going to do some local training. So some stochastic gradient descent, basically like taking the negative gradient direction on your training data TI. And it's going to pop out a new parameter. Each device is going to pop out a new parameter, W hat 1i, where 1 corresponds to, say, the first iteration of this process. And so each device is going to have its own parameter, and then each device is going to send back its parameters to the server, and the server is going to aggregate those parameters to get a new iterate. So here we haven't just taken a bunch of gradient steps on just a bunch of data, as in regular stochastic gradient descent in federated averaging. We took many different trajectories of gradient descent, got many different parameters, one for each device, and then aggregated them on the server. And in this way, the data never left the batch of devices, and we've just sent a parameter to the batch and parameters back. So no, at least raw data was transferred. There's of course still privacy issues here, but we're going to ignore them for this talk for now, apart from the fact that we're not sending raw data. But our algorithms are also compatible with, say, differential privacy notions and those sorts of things. And to actually complete this federated averaging cycle, you're going to sample another batch of devices and basically repeat this process, run local training, get a bunch of parameters, send those parameters back to the server, and average those parameters to get a model. You're going to do this for many batches, say tau, and this is really kind of the iteration complexity of federated averaging, which is each communication round is going to cost some amount, and you want to minimize the number of communication rounds that cost you to, say, train your model, or to, in our case, tune the hyperparameters of this training process. You want to minimize the number of communication rounds it takes to actually do this. And this separation between, this separation between kind of local training and aggregation also lends itself to fine tuning. So once we've aggregated, we can then also fine tune our data on, or fine tune for each specific device. So the original federated averaging algorithm was built in mind with a global training paradigm where one, say, language model works for everyone. We all text the same way. The next word is for all of us is going to be the same. This is, of course, not realistic. You text very differently than I do. And so we might also want to personalize on each device or using the training data on each device, TI. And so sometimes after training, you might also want to see how well you do on personalization when you actually take your global model and train a bit on your local device and use that model on your local device on your individual text messages, because that will be a better way to do it, hopefully. And this separation also leads to a kind of two different types of hyperparameters. So for example, you have server hyperparameters, which is how the server determines, say, how big this aggregation update is, how far it's going to go from W0 to W1. And also the batch size, so how many devices it samples. On the other hand, you also have tons of different local hyperparameters on each device. You're going to see what is the learning rate of SGD here? How many epochs does this SGD run for? So iterations or passes through the data. What is the momentum of the stochastic gradient descent, which is a parameter there? What regularization do you apply, and so on? So there's also a lot of local hyperparameters. And this distinction between server hyperparameters and local hyperparameters will also be important later as we talk about actual hyperparameter tuning in this setup. And so the challenges of federated hyperparameter tuning using an algorithm like federated averaging are threefold, at least as we've discussed them. They have extreme resource limitations. So federated learning has kind of an inherent restriction in computation because oftentimes the devices are weak. They're not, say, a corporate-owned GPU or TPU. They're basically cell phones. These are very weak devices. Not only do they have very weak compute, they also have very limited memory to the extent that you can't even run Atom because that extra kind of per parameter learning rate gives you an extra amount of memory that you have to take up. And also there's, of course, communication restrictions. These devices might be off. It takes a while to transfer these parameter vectors back and forth. And you also have data access restrictions. So like the devices are off or being used and so on. So this is the resource limitation issue. Basically, you can't run many hyperparameter tuning rounds because you just don't have enough compute to do it. Another limitation is that computing federated validation is really costly. If you have, say, validation data per device, the thing you're going to have to do is compute validation metric on each device. And so you're going to have to wait for each device to come online in order to compute the validation score over your entire data set. Basically, unlike in the server setting where all your validation data is in one place, you can just very quickly, just one forward pass through, say, your neural network, compute your validation data or validation accuracy. Here, you actually have to wait for each device to come online to get its validation data to actually compute how good you're doing. And finally, we also care about personalization. And this is, again, difficult because if you want to evaluate how well you're doing in personalization, not only do you have to do all this stuff about federated validation, where you have to access data on those devices, but you also have to do local training just to validate, not just to train, but also to validate. You have to do fine tuning in order to see how well you're doing on personalization. And this is, again, a costly additional local training because these devices are weak, they might be off, and so on. Is the setup clear so far, or are there any questions?
I have a quick question.
Sure.
Is there a consensus on how is it a sequential thing where each device comes online at a particular, in a particular order, or is that basically also a user choice or how the system is set up? And
my understanding is that there's often not very much say that a company, say, might have in what devices are on and off because basically it depends on did the user agree to their device being trained when it's off? Did the user plug in their device when they went to sleep? Is it like nighttime where they are? There's also kind of these kind of very specific challenges to federated learning here that are relevant to your question, kind of what kind of devices, devices are going to be different, or different devices are going to be on or off at different times of the day based on, like, say, where they are, and this is also an issue. But here we're kind of just going to say, you get a communication round, and that's like a batch of devices, and it's going to give you some things. Our evaluations are really going to be in kind of a simulated setting, and we're really, looking forward to actually doing this on kind of a more realistic data with larger data sets and kind of more challenging kind of batches and data sampling issues. Yeah.
Gotcha. Thank you.
Thanks. Okay, so now that I've set up the challenge, and hopefully everything I've said have been mostly clear so far, I'm going to discuss our work on how we're going to actually do hyperparameter tuning in this setting and in the face of all the challenges in this setting. And so in this work, we're going to try to exploit connections between federated learning, hyperparameter tuning, and areas such as neural architecture search, which is a recent area, kind of a subfield of hyperparameter tuning that's been receiving a lot of attention as well. And so in the rest of this talk, I'm going to discuss kind of very basic ways of how we can apply hyperparameter tuning here, and then new baselines that we derive from this. And then we're going to discuss FedEx, which is the approach we come up with that incorporates both neural architecture search, which I'm going to call NAS, into this approach in order to improve upon these very simple baselines from just regular hyperparameter tuning that can be applied to not necessarily architecture search. We're not going to actually study architecture search except via connection. We're going to tune regular hyperparameters here. So that's the outline of this talk, and then we'll have empirical results at the end. So in neural networks, we have kind of these complicated networks that we're trying to learn from data. And the setup of hyperparameter tuning is that we have first a search space. It can be continuous or discrete. So we can have discrete choices like which neural network am I going to use? Should I use a ResNet or a VGG? We can have continuous hyperparameters, which is our learning rate and our regularization weight decay parameters, and so on. Then we have a search method. So how are we actually going to search through the search space? And the first kind of search method we all think of is random search. So impose some sort of distribution on our search space, sample from this distribution, and basically like set some knobs according to just some random distribution, and then have some evaluation of the sample. And the first evaluation method we can think of is running the sample to completion. So fully training this neural network using these settings that we've sampled to completion. And this is, of course, super expensive because we get some error out of this, but it's going to be quite expensive when we have to do this many times in order to compare which architectures are going to do well. And so the question becomes, how can we efficiently actually identify these high quality hyperparameters without going through full training runs of neural networks for each of these hyperparameters. And this especially comes into play in federated learning because we have even more resource limitations. In practice, for these kind of very basic hyperparameter tuning questions, companies have the resources to do hyperparameter tuning. Maybe not on GPT, but on many of the networks we hope to run on cell phones. On the other hand, in federated learning, we have cell phones that are running our gradient descent. We don't have the resources to actually do hyperparameter search in its entirety when we're doing full model training for each hyperparameter.
Quick question here.
Yeah.
So when you're talking about the hyperparameters here, are you talking only about the global hyperparameters or also the local?
I'm talking about both, yeah. So far, I'm talking about both. I think all the examples here are local in this setting, but right now I'm talking about just the regular hyperparameter tuning, probably.
Got it. Okay.
Yeah, so this is a kind of a super expensive challenge of doing this hyperparameter tuning, and it's certainly not feasible in federated learning settings. And so because these kind of very basic approaches are expensive, people have been developing hyperparameter tuning methods that might be better, such as evolutionary search, Bayesian optimization, gradient-based optimization. And with the advent of neural architecture search, there have been even more developments, both for search methods and also for evaluation methods. So one we'll be focusing on is weight sharing. But basically different distinct ways of seeing how well a network is expected to perform without actually training the network or some hyperparameters to completion. And there's kind of a range of how well or how cheap and how costly these methods are, and also how accurate they perform. And then the question becomes for us is, can we use the best hyperparameter tuning and neural architecture search techniques that we know of for regular model training and apply them to federated learning? So remember, these are the challenges we have. So we're going to borrow and adapt kind of these ideas from past hyperparameter tuning to apply them to federated learning. So specifically random search, partial training, full training, and weight sharing. And I'll go into what the things on the right are as I introduce them. And it's going to lead us into kind of our new baseline section. And so we'll put kind of our challenges on this left-hand side on the rows, basically. And we're going to see the competitor methods that we have. So we're going to start with random search. How do we apply random search to federated learning? What are the issues with applying it? Then we're going to look at successive halving, which is an improvement upon random search that's generally viewed as one of the kind of the state-of-the-art methods in hyperparameter tuning. And we're going to see a new method that we introduced called FedEx. So in random search, you have this issue, it immediately runs into this resource limitation issue. You have to fully train all your models. And the other thing is that the federated validation is sporadic. You don't get access to your entire validation data. So because you can't, basically you have to wait for all of your data to be sampled. And so it takes a while to actually get a full validation, fully validate how well you're doing at the end of your run. And also there's this assumption for personalization that kind of you're going to train a global model most likely. And there's an assumption that your global model is also going to be good for personalization. And you're going to maybe sporadically validate how well you do on personalization as you do your random search. And so we're going to see how to improve upon these challenges by introducing successive halving. But let's first look at what random search might do. So here I've plotted basically just kind of an example of a bunch of different hyperparameters, their predictive error on the left-hand side, and then the number of iterations on the x-axis. And we can see, and so we want the predictive error to be small, and we see that a bunch of these random samples, you sample them, and then maybe some of them are pretty good, like like these ones, and then other ones you kind of see immediately are pretty bad, like this red one up top, or maybe this green one. And what kind of the intuition behind successive halving is that a bunch of these examples up top are kind of wasted iterations. You don't want to be doing them. And so the idea is you want to cut off certain runs before wasting too much iterations on them, once you're kind of pretty sure that they're not going to lead to anything useful. And you want to focus instead that your efforts on kind of giving more resources to to settings that you see are going to do well and like early on. There's issues here, of course. The sequences can be non-monotonic, they can be non-smooth, they can be very noisy, and you can't see, for example, at the beginning here, which sequence is actually the one that ends up here. It's very hard to distinguish even visually once we have access to everything at the end. So it's hard to actually safely discard different settings, but in past work, there's been very successful algorithm called successive halving, also known as hyperband, or something kind of that wraps it, called hyperband, that has been has state-of-the-art empirical performance, has provable guarantees, and is used by many different industries, companies, academic labs, software packages, and so on. And I'm not going to get into the details of how exactly these settings are determined. So it's pretty straightforward. But we're going to basically view this as random search plus, basically successive halving, just also randomly samples, but allows itself to give more resources to better settings by removing settings that aren't doing too well early on. So here, if we go back to our table, we see that you gain a bit in resource limitations because most models, they're likely going to be bad. Many settings in federated learning just yield really poor results. So you're only going to partially train most models, and just a few models you're going to train to completion to actually compare them. All the other issues are still there. So your validation is still difficult because you have to validate on many different devices. And again, your personalization is still sporadic.
Quick question, Misha.
Yeah.
So the predictive error is on what exactly? Is it a local validation set, or is it like do you have a test set that you're computing? Like, is that global or?
Mm-hmm. So in this setting, what we're going to do is this is kind of a very hairy issue actually in federated learning, that basically we're going to treat the setting as we want. Each device has a split of training data and validation data, and we want to do well on average across all the devices' validation data.
I see. So it's an average of all the validation
on all devices, all your training devices. So yeah, this is a choice one has to make in kind of the empirical work here, where you could also have like just validation devices, right, that have validation data here. We chose kind of a different approach. Either is valid depending on what your kind of interests are. There is kind of an issue where you don't have access to all the devices at once, and you kind of have to estimate this validation data. And you basically have to do this with any of these algorithms, especially random search or successive halving.
Got it. Okay.
Yeah.
May I know how these two baselines compare to Bayesian optimization?
Yeah, so Bayesian optimization, compared to random search, it's been found that random search is, I think, there's been a lot of debate, I think, on this question. In my experience, kind of Bayesian optimization is good, but it's unclear if kind of the effort required to use it is always better than, say, using random search. Because random search just give maybe a few more resources to random search, and then you kind of get Bayesian optimization, like Bayesian optimization level performance. But there have been, I think, pretty successful combinations of successive halving approaches and Bayesian optimization. So methods like they're called like BOHB, which is BOHB, and so that's been a reasonable method, I think, and that's had some success. And I think they can be used in tandem in kind of that way.
Thanks.
Yep. Okay, so we've seen that kind of these baseline approaches can be applied to federated learning once you've massaged them a bit. But what we actually want to do is get around more of these challenges more completely. We're not going to be able to fully solve them yet, but FedEx will actually, I think, make progress more so than many of these baselines on these resource limitation and federated validation problems. But to actually get through FedEx, we're going to have to go over a bit of the literature on neural architecture search and see what this weight sharing approach, which has been super successful in that domain, and how it can be applied to federated learning. So let's get started. In neural architecture search, you have this goal of you want to find the best architecture in a set script A that minimizes your validation loss on your data. So LV is your validation loss on all your data, and you want to find the best architecture in your set script A that minimizes this validation loss, subject to WA, which is the parameter obtained when you actually train with your architecture on some training set, which we'll just kind of lump into this loss LT, so loss on the training set LT. Subject that WA is a parameter that you obtain by running, say, gradient descent to minimize loss on LT. So you have the kind of this bi-level optimization problem where you want to minimize validation loss on top, subject to minimizing a training loss on the bottom with this parameter WA, and you're trying to find A, which is kind of this architecture, which can be just like, say, the settings of where do you want to put a convolutional layer, where do you want to put a skip connection, how big your convolutional layer is, and so on. And the standard costly approach to doing this is to learn a distinct model weight for each configuration. So basically, kind of as we saw with random search, sample a bunch of A's, so architectures, train a bunch of them, so minimize this internal problem, and then see how well they do on validation. And kind of similarly with federated learning, you run into this issue where training many different architectures is extremely costly. So before this weight sharing technique that I'm going to discuss, architecture search was basically something that was kind of a fantasy that only Google could do. It took tens of thousands of GPU hours. On the other hand, you can also, so this is a bi-level problem, but you can also view architecture search as kind of just solving an empirical risk minimization problem. You can basically solve architecture search by optimizing a different objective, which is just combine your validation and training data and optimize this single loss, and hope that the architecture you get by doing so, and how you do so we'll discuss, is also good. Now, the weight sharing technique kind of comes from this idea because you can use a single set of weights to evaluate an architecture in A. You don't. The key here is that you can change you can update your weights somehow, update your architecture somehow, and still keep the same weights. So they're going to be shared among many different architectures, and you can hope that kind of the weights are going to indicate how well your architecture is doing. And this is kind of the technique known as weight sharing. Basically, you optimize this problem over both W and A, and then you sample many different architectures A somehow, and hope that the W's are indicative of which architecture A is actually the best. And so to actually evaluate a single architecture, you only need to do one forward pass through your data instead of many different forward passes, or instead of full training for each architecture and your weights. There are some kind of constraints here. You have to assume that different architectures have the same number of weights, which is of course not realistic. So like ResNet and VGG don't actually have the same number of weights. But usually what people do is just take the union of the weights, or take kind of the architecture with the largest weights and subsume the weights of the smaller architecture in the weights of the larger one. And the reason we can use weight sharing is that this objective of architecture search, this empirical risk minimization objective, can change for fixed weights, so for shared weights. But just by changing the architecture, this objective will change. Note that this is specific to architecture search because you can't change the learning rate or some other hyperparameter like that and expect this loss to change, because the only way the learning rate or the regularization affects the loss is by changing the W. So if W is fixed, changing those won't affect this objective, but changing the architecture will, because now you're passing the data through a different computational graph, even though your weights are the same. And so this is kind of the technique of weight sharing, and there's now an issue of how do you actually apply weight sharing, because in an architecture search setting. So we want to minimize this objective, which is the architecture search objective. We have a set of architectures A, they're discrete. It's just discrete architecture choices, like where do we put a convolutional layer, and then a bunch of continuous weights. And the issue is that we can't apply our favorite algorithms like gradient descent to discrete objectives. But of course, people have gotten around this by different types of relaxations. The relaxation we're going to be considering is the stochastic relaxation, where A is no longer a set of, no longer a discrete set, but we're now going to enforce a probability distribution over A, a continuous distribution, like say the categorical distribution, that you can then optimize in some gradient-based way. So now you can take the derivative of this loss with respect to both W and A, and you can train some set of fixed weights using both of them simultaneously to use just your favorite gradient descent method. Often people use Atom. And now, in order to see how this connects to federated learning, the way we're going to convert this is to actually state a personalized federated learning objective in a way that maps into the stochastic relaxation objective. So in federated learning, we have some type of hyperparameters, say C, which are local hyperparameters. So this is why the distinction with local and global comes in. And say we want to enforce, we have a distribution over these parameters that we want to evolve, right? So in hyperparameter tuning, we're usually evolving some distribution over our local hyperparameters, or over our hyperparameters of our training process. And what we're going to do here to share the weights is that each of these hyperparameters is going to have the same shared set of weights W, but the way we're going to evaluate those weights, so the way the loss is going to be evaluated, is by running gradient descent using these hyperparameters starting from this initialization W on some training data of a device I, and then evaluating this loss VI. And basically, by summing over all of the devices, this is going to become our new objective. And you can see now that the device I, the training loss, or the training loss that we're interested in, changes as we change the local hyperparameters, because we're now training from some initialization and evaluating on the validation loss of the device. And we can use the same set of weights, so some initialization, to kind of judge how well each hyperparameter is doing. And then we can somehow use the loss scores of those hyperparameters using the same set of weights to update the distribution d theta over those hyperparameters. To put this more concretely, let's go back to federated averaging, which is kind of this default algorithm for federated learning. FedEx, which is the method we're discussing, can be applicable to many different federated learning methods, but for simplicity, we can just describe how it applies to federated averaging. And so remember, in FedAvg, we have this kind of setup where we're sending weights back and forth to the server. So we send weights to about two devices from the server. The devices run some SGD using some settings, and then they send the weights back to the server, and the server then aggregates those devices, or aggregates those weights, and then continues this process. Now, let's say that the SGD process has some local hyperparameters. So for example, the client learning rate, the number of local epochs, the momentum, or the regularization are all local hyperparameters of this process. And then the aggregation process is going to have some server hyperparameters. So for example, the server learning rate, how far we move from WT-1 to WT, or the batch size. So how big, how many clients we sample at each communication round. And in this way, we're going to combine FedEx to actually tune these local hyperparameters by sampling from some distribution over some number of hyperparameters that we're going to keep, d theta. We're going to sample C from this distribution, and we're going to compute the validation loss on the device. So remember, as I described in the previous question, we kind of have the split on each device. We have some training data and some validation data. So for each device, we're going to sample some hyperparameter configuration from some distribution that we're going to be updating. We're going to run SGD on the training set of that device from the shared initialization and get out a new set of weights, and then compute the validation score on that new set of weights using the validation data on the device. And the way we're going to actually update this distribution d theta is using an algorithm called exponentiated gradient, which takes in both the initialization and these losses and basically gives a multiplicative update to a categorical distribution over the device settings. The precise kind of configuration of exponential gradient is not that important. You could, in principle, apply many different type of kind of distribution updating algorithms here, possibly even a Bayesian updating algorithm. But we're going to basically use d theta as a categorical distribution, and the natural way of updating this categorical distribution is using an exponentiated gradient algorithm. This is similar actually to a neural architecture search technique that we introduced in a previous work that's called Gaia, that I can also happy to discuss if anyone is interested in. But here you can see that the model weights are shared because we're using the same initialization to update same initialization for each SGD in a batch, each run of SGD in a batch. But then they're shared between a bunch of different hyperparameters over which we're maintaining a distribution. And these settings are then going to be the settings of SGD that we're going to evaluate how well they do using different validation losses on each device.
Quick question here. So
Yeah.
you said that instead of the categorical distribution, you can also have other distributions. So for continuous variables right now, are you enforcing a categorical distribution, or are you?
Yeah, that's a great question. We considered doing some kind of continuous distribution updating, but we found that it worked reasonably well if we basically say we have like, a couple different either categorical or continuous variables. We sampled some number of settings, say 64 settings from the devices, or sorry, some number of settings from these kind of the union of all these hyperparameters, and then we had a categorical distribution over those 64 different settings.
I see.
So there was no continuity there. Everything was discrete. But there was definitely kind of an alternative approach you could take where for the discrete hyperparameters, you run something like exponential gradient, you update the categorical distribution. For the continuous settings, maybe you have like a beta distribution or something like this, and you update that using some other method, maybe a Bayesian method, natural gradient, something like this.
I see. But then if you have enough, I guess in your case, you use 64, and that might probably be enough for many of the continuous variables as well. So is that why you got a good performance, or is there any?
Yeah, I think we were able to get reasonably good performance with just kind of not too many, but also not too few kind of discrete samples. Because in certainly random search is kind of is not easy, but once you get kind of enough random samples, usually at least a few of them perform well. And so this was sufficient for us. Yeah.
Got it. Okay, thanks.
Thanks. And so so this is basically to summarize the FedEx algorithm. We call it FedEx because it's federated, and you have an exponential gradient updating step for actually updating the hyperparameter tuning, hyperparameter settings. There are additional benefits of FedEx that I won't discuss, at least in the talk, but I'm happy to also discuss those. But basically, there are provable guarantees that you can show for this algorithm if you connect this to meta-learning theory. So another framework that we introduced a couple of years ago now called Aruba, that basically justifies different meta-learning and federated learning algorithms in the context of how well you do on personalized data when your devices share some sort of similarity. So task or client similarity is going to be the same here. And basically we show that FedEx is kind of a correct algorithm in some sense if you're interested in just learning the learning rate. So unfortunately, we can only do theory for learning the learning rate, but because it's the simplest kind of hyperparameter we're interested in, or we can learn. But the algorithm we actually use to learn the learning rate can be applied to any hyperparameter that's local. And so that's kind of the benefit here. You kind of get theory for one of the hyperparameters, but you can tune any of them. But this algorithm, one drawback is that it does assume that the server hyperparameters B, so the aggregation hyperparameters, are fixed. And so actually the way we're going to get around this problem is kind of very simple. we're going to run FedEx just to tune the local hyperparameters, kind of boost the tuning of them using this approach. But on kind of the global level, to tune these global hyperparameters B, we're just going to use successive halving. So the algorithm we discussed before, we could use random search too. Basically run a bunch of different runs that have a fixed B, and with a fixed B, check how well we're doing, or use FedEx to tune the local hyperparameters, and then check how well we're doing for each B using something like successive halving. So basically, we're going to use successive halving as a wrapper algorithm around FedEx. Yep.
Sorry, quick question. Maybe you might want to answer this in your discussion afterwards, but is there a reason why your FedEx cannot itself be a wrapper? Like, why do you need to use successive halving?
So the reason here is that kind of the formulation of FedEx depends on this split on of the validation data between training devices, or training data and validation data on device. It kind of depends on there being kind of a meta learning component to, you have a fixed initialization, and you run some setting from your initialization of some local hyperparameter setting from your initialization to check how well that local hyperparameter setting does. In principle, you could think of doing this for global hyperparameters. It's just that there the training run would be like a full run of something like FedEx, and that's super expensive and it's basically not, I guess, the problem we're interested in solving. We're interested in kind of exploiting the fact that we have to send a bunch of send a bunch of parameters out to a bunch of devices, and kind of do local training there, and kind of exploit this kind of issue in order to resolve the other federated issues.
Got it. Okay.
It's definitely a huge kind of interest practically to also be able to do something interesting for global hyperparameters, which are also important in federated learning. You can have a lot of local hyperparameters, but also people are interested in global hyperparameters as well, because everything is expensive here. You want to tune everything as quickly as possible.
Got it. Okay, thanks.
And yes, of course, as I've been saying, kind of we've discussed mostly the FedAvg application of FedEx, but as we discuss more in kind of the paper, and I'm happy to discuss this as well, FedEx can basically tune any method that decomposes into running some local training like SGD on device, and an aggregation step, which say averages the outputs or does some other more fancy computation. And there are many methods that can be kind of summarized as these can be decomposed into these two kind of routines, of which we can optimize the local hyperparameters, but not the global ones. And so this includes FedAvg, but also FedProx, the meta learning method Reptile, and a bunch of recent federated learning methods like Scaffold, FedDyn, Ditto, and FedPA. And so to kind of complete this table, finally, we've introduced kind of this method FedEx, which trains a single model per server hyperparameter configuration. But we don't, basically for individual local hyperparameters, we only have to train one model. So you don't have to do, you don't even have multiple models for any server hyperparameter configuration. Of course, you might have multiple server hyperparameters, but at least you've kind of accelerated your training on top of successive halving by limiting the kind of repetitive nature of training many models for different local hyperparameters. The other advantage we have is that you have continuous use of your validation data. So instead of kind of using your validation data just to select the best model or select the model to eliminate every many rounds, in FedEx, you're using the validation data constantly by updating your distribution at every communication round using the training data that or using the parameter that you update using the training on that device. You then use that device's validation data immediately to update some set of hyperparameter weights. Unlike in these past methods where you use the validation data only when you have to eliminate, which might be after many communication rounds. So that's why we have sporadic use of validation data before, and now we have a kind of constant use of validation data. And also with personalization, we are also constantly running the kind of this personalized subroutine. We're checking how well we're starting from a global model and checking how well any of these hyperparameters kind of personalizes your data or personalizes your model to the device's data. And so we're constantly doing this personalization, and so we're constantly evaluating this personalization using our constant validation evaluation. Okay, so now that I've discussed our method, let's see how well it actually works. And this is kind of a short section based on some simulations we ran, although we did run simulations on 3 different data sets. We considered 9 different hyperparameters, 2 servers, and 7 client hyperparameters. Specifically, the 7 client hyperparameters would be something like learning rate, momentum, regularization like wet decay. Using these hyperparameters, we encompassed 3 different federated learning methods. So FedAvging, of course, FedProx, which is basically 1 extra hyperparameter of how much you're regularizing to how much you're upweighting kind of a proximal term. So that's just a continuous hyperparameter in addition, and Reptile, which is an extra server hyperparameter. Each method that we're comparing, so we're going to be comparing successive halving, random search, and then successive halving and random search wrapping FedEx. So our goal will be to just improve on kind of the training local hyperparameters using FedEx. Each of these methods is getting a fixed time budget and evaluated on 3 data sets. One is CFAR10, which only has IID tasks, basically split along, basically sampled different classes and have binary classification. And the others, which are the Shakespeare data set and the FEMNIST data set, are non-IID, and they're kind of crafted to be so. And to actually see how well we do, we see on the left we have the error, and we have the 3 data sets here. So random search on its own does reasonably well, actually. Like, this is reasonable error to obtain on this data set. It's not great, but it does not non-trivially well, even though we didn't give it that much more resources on top of a full training run. We successive halving gained significantly on all of the methods. It improves significantly upon random search, which is great. But then when you combine successive halving with FedEx, what you're going to see is that additional improvement upon successive halving, at least on Shakespeare and CFAR10, the improvement is significant. On FEMNIST, the improvement was less. Overall, what we've seen from kind of this first approach to federated hyperparameter tuning is that even this relatively simple method like FedEx that only applies to local hyperparameters gains kind of a similar lift that other weight sharing methods in neural architecture search have gained over the random or like successive halving baselines in architecture search. Similar, like basically the performance gains are similar in this federated learning setting with regular hyperparameters as they were in the architecture search setting with architecture hyperparameters. Of course, these tasks are pretty small, and we're looking forward to working with some people who where we can evaluate them on bigger tasks, more real-world tasks where the data is generated from more interesting distributions, more challenging kind of batch settings, communication settings, and so on. And the key takeaways, I think, from our talk is that we've identified some challenges and initial baselines for the setting of federated hyperparameter tuning. So we saw the difficulty of kind of the extreme resource limitations, the validation issues, the personalization issues that you have from in this federated setting. And we've also introduced some baselines for handling a few of those. And then we introduced this method FedEx. We did some theory for it. We kind of connected it to this state-of-the-art methods for architecture search, and we've shown that it does improve over these baselines. So with that, I'd like to conclude my talk and thank the organizers for inviting me. I really appreciate it. If you want more information, my website is here. Kind of the buzzwords for the various kind of papers I've discussed are here also. And then, of course, my collaborators, Renbo, Tian, Liam, Nina, Virginia, and Meet. So thank you, and I'm happy to answer any more questions.
Thank you so much, Misha, for the great talk. Let's give Misha a round of virtual applause. And yeah, is there any question from the audience here?
I can start with a question. I've been asking questions throughout, but so I was kind of curious in your evaluation setup. So you said that you had a fixed time budget. So did that mean like you evaluated on different resource settings also, or were they basically the same resource settings, but so essentially were the devices kind of identical in the simulation, or were they different? And would this time budget effectively like affect if the device resources were different?
So that's a great question. I think perhaps I should have said the time really here is just communication rounds. So the resource here was one communication round, which kind of abstracts away all the issues you're describing with device weakness and so on, or like availability. I think those are kind of interesting questions of whether there's no real reason I can see that this method wouldn't at least adapt to those settings, but certainly evaluating in the settings would be important.
Got it. Okay. Thanks.
Hey, Misha, I have one quick question. Like, it seems that you were just showing the comparison on the different data set. Have you also compared with like other federated learning environments?
We haven't looked at, I don't know exactly which environments you might be referring to, like different like TensorFlow or PyTorch kind of things.
Yeah, the Clara or other platforms that has their like normal averaging on the federated learning scheme.
No, we haven't looked at those. We've basically just worked with simulation data. Yeah, we are working kind of actively on using kind of a bigger platform to evaluate on bigger data sets, but this is kind of an initial pass.
Okay, makes sense.
Thanks.
I have one other question also. So it was interesting that the most gains that you had in your 3 data sets were on Shakespeare and CFAR. I forgot if you mentioned Shakespeare was IID or non-IID, and would that kind of affect, like, did you in your experiments kind of see that this works better in IID settings versus non-IID settings?
So CFAR was the fully IID data set, just because there are ways of constructing IID data from CFAR, but we didn't consider those. Shakespeare is non-IID. It's non-IID in kind of different ways, both the tasks are non-IID, and also we consider kind of the temporal dimension where the training data was like the first parts of the play, and then the validation data was the last parts of the play, which at least is non-IID in that sense, temporally. It's unclear to me why those 2 data sets this method did well on. It might be that FEMNIST is just kind of maybe hard to do much better on with kind of the resource settings we have in our specific setting. Yeah, it's I don't have a very good explanation for why hyperparameter tuning did better on those 2, but yeah, it's probably not we didn't really see, I guess, a pattern.
Got it.
We did also check, for example, like whether more IID Shakespeare, like, the IID version of Shakespeare, whether there was like a distinct difference, and overall we saw that still FedEx improved there over successive having more so than on FEMNIST.
Got it.
Yeah.
And a follow-up from that, could you comment about the heterogeneity present in each of these data sets? Were they like, were the samples in the Shakespeare data set like pretty homogeneous compared to what you might expect in a real world distribution? I'm just trying to brainstorm about what could there be something that could explain why this difference could be seen.
I guess Shakespeare, I think, is probably the most challenging data set here, and also, it's the only text data set here. Shakespeare, the data set was less homogeneous. Some devices have very little data because, like, some actors or characters didn't get much to say. Whereas I think FEMNIST and CFAR 10 are less challenging, certainly CFAR 10.
I see.
I don't know whether Shakespeare was more heterogeneous or not than the others in any kind of way that I can kind of quantify, really.
Got it.
Yeah, it's definitely kind of interesting why, what causes these different, like what causes this method to do better there. Yeah, it's unclear.
Sounds good. Thank you.
Could you elaborate more on how when you do weight sharing, how do you how they done for models that have very different architectures, like VGG versus ResNet? They are actually quite different, right? So how do you do the weight sharing there?
Right. So that's a good question. One thing I have to confess is that ResNet and VGG are kind of just toy examples here for maybe a non-architecture search audience. We don't actually ever search between ResNet and VGG. I think that's more of a hyperparameter choice. Practically speaking, in architecture search, what we do is we try to design cell structures, so kind of repeated blocks of a network that we then stack on top of each other. So, for example, like one kind of very successful cell structure that one may hope to discover is like a ResNet, right, where you pass like one path of the data is through the convolution and the other path is through a skip connection. And then you kind of have binary choices on all of these edges of where do you put the convolution, where do you put a skip connection, where do you put an average pooling, something like this. And what kind of convolutions, so like 5 by 5 or a dilated convolution, and so on. And there's two ways of sharing weights between these different operations. One way is that you give each operation its own weight, and then evolve them simultaneously, but you give them its own weight. This works okay, or this works okay, and it's basically what people do. Something that works worse is if you give each operation kind of the same weight. So like say the largest convolution people consider is the 5 by 5 convolution. So that's going to be like the largest weight. And then its weights are going, like the weights of the 3 by 3 convolution are going to be part of the weights of the 5 by 5 convolution. So you're just going to recycle those weights somehow. And then you're going to use those. And people don't really use that because it kind of leads to the weights conflicting with each other. Yeah.
I see. Thanks.
Yep.
Is there any other questions here? If not, let's thank Misha again for the very interesting talk. And we will post the recording of this video later to our YouTube channel. And if you have further questions, feel free to reach out to us too, and we will connect you with Misha later. And thank you everyone for joining us today, and see you next Thursday.
Thank you.
Thank you.
Thank you. Bye.
Bye-bye.